The next talk will be given by Marshall Eubanks on time metrology and fundamental physics on the lunar surface.
Thank you very much. So the next slide, obviously. So I was wanting to look at timing in the context of decadal survey, where we're trying to look at decade or more. And also because I think that there's something that's been going on in the timing community that not a lot of people maybe recognize. I mean, Slava and others have gone over what you can get from the moon from ranging, from lunar laser ranging. And obviously that can be improved with better lasers and better retroflectors and so on. I'm actually been working on VLBI beacons and something called Compass with the idea of connecting the moon better to the celestial reference frame and doing transverse thing. But there is the transverse position of the moon and its rotation and so on. But there is yet another way you can use that is now just becoming possible. And that's the path of time. And that's through timing. The next slide, please. So this is a graph that shows the improvement in so-called microwave clocks, which are the atomic clocks most of you are probably familiar with. A cesium clock is a microwave clock. The transition is in the microwave. And there's been a tremendous amount of work done on that. And you can see this is the long-term stability and this is from a paper on a focus, which is a proposal to launch a good clock in orbit. But you can see how the microwave clocks have been going down. And they've been going from like 10 to the minus 13 to 10 to the minus 15 or 16 right now. But you can also see that the optical clocks have been phenomenally improving. And the reason is very simple. It's the timing accuracy or the timing stability is to some degree determined by the frequency of the oscillation. The optical clocks are using optical frequencies with laser combs to measure them. The optical frequencies are 10 to the 14th hertz or something like that, much higher than the gigahertz range that the microwave clocks were in. So, in a sense, and I'm not, I think the Deep Space Atomic Clock is great. I think the Pharaoh is great. I'm very glad that one is flown and one is supposedly about to fly, but they're being overtaken by events. Now, this optical technology is not close to being flight ready, but I think
some hot mics, please kill them off.
Well, that can't be directed at me because I'm the one talking. Next slide.
I know.
Generally, it's directed at me because I tend to be unmuted, but not this time. Did the slide transition? Because I haven't. It's still showing. All right. So my contention is that the real future of timing and optical clocks will be in space. Next slide, please. And the reason for that is very simple. The Earth, our planet is just not very stable. Okay. And the Time Lord's definition is a big ball of wibbly wobbly timey wimey stuff. And so the next slide, please. On the Earth, a millimeter vertical motion is going to cause a clock fractional frequency change of about 10 to the minus 19 seconds per second. And that's within the reach of optical clocks now, I would contend. And anybody who's done geodesy, as I have, knows that it's really just not realistic to think you're going to be modeling the vertical motions of the Earth to a millimeter level or better, probably ever. And the reason is just we have too many things moving around. I mean, for example, in Washington, D.C., one of the big changes is the currents in the Chesapeake, which are 200 miles away or so, Chesapeake Bay. And, yes, so you can do things. You can have gravimeters. You can have something like Grace flying overhead, but it's just going to be very, very tough to model this to much better than a millimeter vertically. And that suggests you're going to have a limit of right 10 to the minus 19. On the moon, a millimeter of vertical motion is 5 times 10 to the minus 21. And the moon's a much easier body to model. It has not got oceans. It has not got an atmosphere. It doesn't have a lot of mass moving around. There's no snow and none of that stuff. Everything is slow. Well, we think mostly. There's an asterisk, an exception there. So my contention is as the optical clock technology improves, the clocks will move into space. They'll have to. And really the logical place to put them is for long-term use is on the moon. For a time scale is on the moon. Why is that? Because if you put one in orbit, you got to move the thing around. It'll have accelerations, it'll have vibrations, and that will also limit its use for long term. If you want to do a comparison like focus, that's fine. But if you want to say the timing is now being set on the moon or in space, it's likely to be on the moon. Next slide, please. By the way, the use of the clock to determine the sort of the mass concentration and movements around you is called chronometric geodesy, and I think that's going to become a big thing. So this is just a optical lattice clock observation of tides on the Earth, and you can see that they're varying around at 10 to the 17 level, and that's a lot. Now, yes, these are periodic, these are tides, but there's ocean tides in here too, and for that matter, also atmospheric tides. It's going to be hard to model these at the 1% level. Next slide, please. This is a comparable thing for the moon. The moon has a big static tide, of course, because it's geostationary in that sense. It's pointing at the Earth all the time, except for librations. And so the static tide, or where the various latitude lines here are, biased. But you can see it's a much quieter environment. The monthly tide is the big thing. There's a fortnightly and a monthly tide. Those are the big things. It's also annual and 18.6-year tide. And again, there's not a lot of subsidiary mass motions. So although the potentials are comparable, I think the moon's going to be much better. Next slide, please. So I've been thinking about this a fair amount. And if you're going to use timing, and actually this is coming very quickly because people are wanting to set up PNT networks on the moon, and they're wanting to set these PNT networks up using data from Earth, using data from GPS, and they want to have it all run autonomously. Next slide, please. I think you're going to need to adjust your time. And that's actually, done. It's something that a lot of people don't like, or some people don't like, but it is done. So, for example, atomic time and TAI, the time we use, the time that UTC clocks are really running at, is actually offset from the geocenter. Of course, the geocenter is a fictitious thing. There are no clocks at the geocenter, nor will they ever be. And it's offset by this fairly long number. Dennis McCarthy and company came up with 6.9 times 10 to the minus 10. And so the surface of the Earth is redshifted compared to their geocenter. All right. So JPL, Miles Standish, didn't want to change, and he actually, pretty good reasons, didn't want to change the ephemeris time over to the coordinate time at the center of the barycenter, or the center of the solar system. And so JPL development ephemeris run on barycentric dynamical time, which is redshifted, again, away from the barycenter itself to run at the same rate as TAI. So there's no buildup of time separation. You just have periodic terms, which are pretty small. GPS clocks are famously adjusted, I believe, in the factory to run, they are redshifted by this rate of 4 times 10 to the minus 10. So they appear to run at TAI rate here on the surface of the Earth. Next slide, please. So I think that's going to be done for the moon. I think we're already sort of slipping into that because people are thinking of using GPS. Now, GPS from the Earth has low SNR on the moon or near the moon, and it has a horrible geometric dilution of precision. But if you can determine where you are from LLR and VLBI, you can use the GPS as a timing signal because you don't care about the dilution of precision there. You know where you are. You're just trying to find out what the clock difference is, and that you can do. And so I think it's going to be used. And so I think what people will do, and I just wanted to bring this out and make it explicit, is I think they will adjust the lunar time effectively to run at TAI rate. And I think spacecraft do that already. I believe all the Martian spacecraft actually run on at a TAI adjusted rate like that. But they do it sort of informally and unofficially. So in case here I go through the numbers. And if you do that, you're gonna have to the lunar time is blue shifted, which means you'll have to redshift clocks about 6.54 times 10 to the minus 10. And the biggest periodic terms is anything lunar, you have lots and lots of periodic terms because you've got the moon and the sun, you've got the Earth and the sun and interfering with things. But the biggest one is the so-called equation of the center, which is just the elliptic part of the moon in orbit, and that'll amount to about 400 nanoseconds integrated over a month. And I'm in the process of integrating all of these things to figure out all the timing signals. And it's just, there are a lot of them. They're all going to be smaller than that. So that's about 100 and something meters. So that means,
5 minutes.
thank you. If you don't care about things to better than 100 meters, you're okay. So I think this is going to happen. I think this is going to be inevitable. And I just wanted to bring this up, have people start thinking about it. Next slide, please. All right, next slide still. So one of the things I've been interested in is gravitational radiation and what you could do with lunar optical clocks. And somebody mentioned this in the earlier, maybe it was Slava, in the plenary talks. There's a couple of interesting things about the moon. It sits there about 1.5 seconds away, of course. That means that its sensitivity to gravitational waves will in some sense be best for waves with a frequency or period of about 1.5 seconds, hertz or so, gravitational waves. It happens that that's in a hole between LIGO, advanced LIGO and Virgo, and the upcoming ELISA, which not supposed to fly now to 2034, so it's going to be a while. But even when these things are both flying, they won't do a very good job in a second. And so I think the moon and the gateway with a good clock there could actually do something with gravitational waves in this hole, which would be sort of heavy, intermediate mass black hole mergers, 1,000 solar masses, that sort of thing. And the difference between it's a little different. If you're looking at doing gravitational radiation with ranging, with timing, in the other sense, you need to model what's going on at the measure. And since you're trying to get 10 to the minus 18 or 10 to the minus 19 strains out of the system, that means you're looking at really tiny motions, which is why LIGO has this elaborate, multiple pass Michelson interferometer and so on and so forth. But if you're trying to get time, you just need to model the velocity sort of to that level. And that's a lot easier. Next slide, please. So I think that, the potential exists here in the next decade to start really actually trying to do some serious modeling of gravitational radiation with an optical clock on the moon, ideally multiple optical clocks. And incidentally, you'll have a very interesting Sagnac effect there too. So next slide, please. The next slide should be the last slide. I'm not seeing. Oh no, just skip over this slide. So I wanted to bring in front of people's attention the possibilities of using optical clocks in space. I think there should be a decadal survey paper on that. I'd be glad to take a role in that. Anybody who's interested should contact me. I think a logical place to put the clocks will be the moon, because I think you're going to want, at least for a time system, you're going to want to have a place where you can put clocks where they don't move around and they last a long time. Sort of a naval observatory on the moon. I think there are going to be many uses of these clocks. I think they're going to be usable for PNT, obviously, the position, navigation, and timing. I think they're going to be usable for the Odyssey type things, as I mentioned. I have some things I hope to talk about at the Interplanetary Science Conference on this. But they're also for fundamental physics. I didn't even go into the gravitational redshift because that's kind of obvious. With a good optical clock on the moon, you can measure the gravitational redshift for something like 5 orders of magnitude better than we do now, or we'll do with Faro. So, and I think that, with the missions that are planned to go to the moon and the economic sort of development that's possible with the moon, we need to start thinking about setting up a lunar time scale and what that means. And so I sort of went into that. So that's it. Thank you very much.
Excellent. Thank you very much, Marshall. There was a question in the chat, which is, how does electronics respond to such small clock times of 10 to the minus 15 of a second?
Well, okay, so in the timing community, one of the little secrets is all clocks are quartz clocks at high enough frequency, because all clocks are really a quartz oscillator that's being driven by some other thing like a maser or cesium or an optical clock or whatever. And so if you're talking about how do electronics respond to, say, at a second, well, actually they tend to be worse than this. Those are stability numbers I was showing, not like 1 second time. Now, that's a whole other thing. We can go down invariances, and I have charts here that I could show and so on. But the answer to that is at the second interval or 10th of a second or whatever, they're not really. And in fact, the best clocks may still be hydrogen masers, which are good to like something like 10 to 14 or 10 minus 14 or so at 1 second. But if you start talking about it a day or a week, then the fractional frequency stability, the actual changes in phase are larger. And so the electronics, which can easily, nowadays we can easily measure things at the picosecond level. And so you can just work out what that translates to get to 10 to the minus 18 or 10 to the minus 19 or whatever. So
Excellent.
it's not actually a problem.
All right. Marshall, thank you very much for the presentation.